Hello everyone, welcome to our 12th lecture. I'm so happy that you are watching this lecture. The topic today is going to be mass energy in control volume systems. Before I continue and talk about this lecture, I would like to say that this lecture is going to be kind of long because we're going to cover I want to cover um, in detail this topic to make sure that you feel comfortable and you feel deep in understanding this topic, because in future, if you continue on like fluid dynamics or thermodynamics in your job or in academia, then you're gonna face this like flows and stuff, energy coming in, mass coming in or leaving the system. You need to specify all these characteristics and properties of your system. So I would like to spend enough time, so I will go quickly on the blackboard. First of all, so here's our page, and in content, let's look at our lecture schedule that has been updated. So in January 12 and 13, here's the topic, and then I've posted lecture number 9 and 10 online. These are the corresponding sections of chapter 5. The assignment number 4 has been submitted, and the solution will be provided after 24 hours, so that's going to be like today at 8 a.m. Well, so yeah, everything is online, the new lecture videos. And now just I want to be quick to save time, and here is the example that I'm going to talk about in chapter 5. Here is the first example. It's a heat exchanger, here number 1. And as always, please keep this in front of you on your screen, because I'm gonna talk about the figure and the numbers a lot. Thank you for that. So let's go to my notebook. So so far, so before I start to solve this example, I need to give you some equations, and we need to talk a little bit about the concept of this subject before we go and solve our examples. So far we have covered some topics like manometers, that was mainly about hydraulic pressure and forces. And we talked about piston cylinder devices like that are in the category of closed systems, so we had specific amount of mass, and then we applied like a work, heat, and then we measured pressure, temperature, or any property of our system. Then we moved on, and then we solved examples in open systems. For example, a pump, that was an example. And or we mixed like a pump with the pure properties of a pure substrate, like saturation points, superheated or subcooled states, and we covered the process and stuff. So um, let's say like in general we were talking about closed and open systems, right? Great. So if I divide and if I draw the typical um, like figure about these two um, systems here, I would have closed system, right, on the left side, and on the other side I have an open system. So this system would look like that. In the closed system, we have straight solid lines which represent our real boundaries. They are real boundaries, and we had like a mass, specific mass of my system, right? And then I applied, for instance, heat, right? Or we do like work on the system, and we solve for pressure, like initial or final pressure, or temperature, hope you remember, or like volume, or even if we mix this system like a piston cylinder system with kind of a uh, uh, let me check this guy, okay, with like properties of pure substances, then we will check the quality as well. Okay, so that was simple. On the other side, we talked about open systems. So in the open system, we have a combination of solid lines which represent again the real boundaries. It's like a casting, like the shell or the boundary of like a turbine or a pump. And we had these dashed lines on, let's say, both sides, on the left and right side, in most of the time. And we had mass, let's say mass flow rate, so m dot means per time, coming in, and we had energy as well coming in, and on the other side we had mass out, leaving the system, right, and energy leaving the system. Or we could like add energy by heat or work, electric work or shaft work or any kind of work. So we could add this E dot as well, which was like external energy, right? And then we solved for properties. For instance, let me divide these guys. So, and then we solved for like m dots, in or out, or p out, or qualities, inlet and outlet, or velocity, right? Inlet and or outlet. So they were the these are all the typical properties that we solved for. Okay. And in the most of the cases, we were using first law, right? So first law of thermodynamics told us that the rate of energy, still it tells us that this energy coming in minus the energy rate going out equals the change of the energy, internal energy in the system per time. For example, we talked about mechanical energy. If you check your lecture notes, you'll find that we had this equation which says E dot mechanical equals the mass flow rate times all these sort of energies per mass, which was like pressure divided by density plus V square, here's the velocity, divided by 2 plus the potential energy due to gravity, so GZ, right? So in this way we solved some couple number of examples, right? Now we want, so here still I'm talking about open system. I'm still talking about an open system. When you see m dot here, it means there is a flow coming in or leaving the system. So the system should be open. So first law, when you refer to first law, is a combination of different energies. So these two E dots, these guys represent a different types of energy. Okay, like here you see GZ, this is potential energy, right? So I had this guy here, let's say here, so potential energy, which is like this Gz parameter is represented by Gz. Or we have kinetic energy, which is represented by V squared divided by 2. Okay, and these two, I'm gonna add two more here, but hold on a second. So all these energies are carried by mass. If you check the system again, I divided two types of systems. Sorry, two types of energies. This guy and this guy. The left one, E dot E, is coming into the system, and the other one is leaving the system. And these two are passed, or they're passing through a imaginary boundary. These dashed lines are imaginary. Okay, but we have another E dot, which is this guy, and this guy is passed through a real boundary. So I can divide these different types of energy that First law tells us. I can divide it into two categories. This is the first one, which are carried by mass, and they are transferred through imaginary boundaries. Okay, which are the inlet and outlet, those dashed lines. So mass is coming in, and mass has potential energy, Gz. Mass has kinetic energy. The molecules have velocity, right? So when they come into our system, they carry this kinetic, this momentum with themselves into our system, and likewise they can leave, they can carry out this energy with themselves. Okay, and we have another category, which are heat Q dot, and work. So work, either like W dot shaft, like in turbines and compressors we have the shaft, or like fan, or we have W dot electrical, like a heater or a resistor with like electric current in it. You have seen those examples. So these are transferred. These are not carried by mass. Not carried by mass. And can you guess where do they pass through? How do they enter our system? As you can see here, they enter, this is square, they enter through the real boundaries, like a piston moves and does work. Or you put like a fire under the piston, under the cylinder, so you're transferring heat from underneath to the gas, to the content of your cylinder, right? So they are transferred through real boundaries. Okay, great. So that's it. So we have covered here all different types of um, all different types of energies that can come into our system or leave our system. I forgot to tell you that here for closed and open system you can check out lecture number 9, page 2, and here lecture number 3, page 8. Okay, so once again I have divided the E dot, the energy coming into our system, transferred in or out of our system, into two different categories: carried by mass or not carried by mass. The category which is represented by like carried by mass, they transfer through imaginary boundaries, right, those dashed lines, and the other one is through real boundaries. Here I would like to add two more types of energies that are flow energy okay, which is PV, right, and we have internal energy, which is represented by U, which is only a function of temperature. For this guy, you can check lecture number 3, page 5, and here for flow energy, please take a look at number 9, page 9. Okay, great. So what are these two types of energies? The flow energy is, let's say here in your here at the inlet you have a gas, you have the fluid that has specific amount or the amount of value for pressure. So you can kind of like think about it this way, that when this flow is coming into the system, this pressure is moving everything in front of it toward our system. So it's kind of like pushing, like going in, going, come on, like push, right? So it's doing work, right? So it has some sort of energy that is entering our system. And likewise at the outlet, if you take a look at those lecture notes, you will it will be more clear. And we have internal energy that imagine this is gas is coming in, it has velocity, that's fine, kinetic energy, it has potential energy, okay, gz, gravity, and let's say we are taking pressure into account, okay, great, so here we have pressure, that's fine, but still these molecules, they have like internal interactions, right, between themselves. It's like rotation or vibration or draft, like kind of internal movements of these molecules. They hit, they collide, and then they rebound, and they do some stuff, right? And the combination of all these energies, like vibrational, potential, like the bonding between the molecules, or the velocity that they have, the internal velocity. It's not the kinetic velocity. It's not this velocity. This is the overall velocity. We're not talking about that. We're talking about the interactions, the molecules between themselves. And that the combination of these three types of energies is called internal energy. Okay, so at this point I can step further, I can go further, and I can modify the first law. Here, see, the first law is just, what is it here, this E dot mechanical that we've been using so far, it just has pressure and velocity and g. What about internal energy? What about interactions between molecules? What about temperature? What about the pressure that it's doing work? So how can we incorporate all these new types of energy that now we are learning, right? So we wanna involve those energies in our solutions as well, right? So at this point we modify the first law. Hmm? So we define the total energy. This is like the most total. This is the last step. I promise I'm not gonna modify this once again. It's that's it. Total energy. Yeah, I'm not gonna. No, I'm not gonna modify this again. Total energy of flowing flow. Okay. Please take a look at number 9, pages 10 and 11. Thanks. So this is how we define this guy, the total energy. First of all, we take theta as the notation, and it's defined per mass. Okay. And it equals U, internal energy, which is a function of temperature, plus, in order, I just want to write them in order: internal energy, flow energy, potential, and kinetic, right? Plus flow energy, P little v, be careful, it's little v, plus potential energy plus kinetic energy. And at this time we can define a new parameter, which is the combination of internal energy and flow energy, which is called enthalpy. Okay, great. And it has to be a function of temperature and pressure both together, because we have pressure and temperature in those two terms, and I call this enthalpy, right? So whenever we talk about enthalpy, keep in mind that we are incorporating internal energy and flow energy at the same time. Okay. So that would be like this as well. So H, function of temperature and pressure, plus, now the rest of it is easy, PE plus KE. That's it. Or I can write it in another way: HT as a function of T and P, plus the potential energy was G. So I'm gonna switch them. So V square, or no. Okay, potential is GZ, plus the kinetic energy is V squared divided by 2. Okay, great. Now, if you remember, I talked about open systems. In open systems, we have rate of energy coming in per time, not per mass. This guy theta is per mass. I don't care. It doesn't help. I want something feasible. I want something that I can understand. And what I understand in my systems, in an open system, okay, in an open system, I understand rate of energy. Transferred per time. Please pay attention. Per time. This is what I like, per time. And that would be E dot. This is C. Look at that. Guess what? See? I was looking for E dot and I'm just struggling to get back to E dot. This is how I do it. I multiply this M dot, which is mass per time, times energy per time. So sorry, energy per mass. So masses cancels out and then cancel out, and then I end up with energy per time. So M dot times H again as a function of temperature and pressure, so we need to go to the tables to find proper values for enthalpy, plus Gz, right? And the unit is what? Is like kilojoule per time per second. It's its power, right? And this guy is which category? Please, 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 please pay attention. Here, I divided E dot into two categories. The first one was carried by mass. The second one, which is heat, which contains heat and work, is not carried by mass. So all these four types of energy that I have here I have took care of are carried by mass. So I would add like E dot mass. Okay, and these are carried by mass, right? Now I want to give you the very modified, like the most modified first law, which says, again, let me tell you once again, E dot in minus E dot out equals dE divided by dt. And we know that in steady state processes, dE over dt equals 0. There's no change in the total internal energy. If you check the total internal energy today, you go home and come back tomorrow, that's going to be the same value. Therefore, E dot in would be same as E dot out, and E dot is here, these two E dots are the total energy. And as we have defined up there, the total energy should be the summation of all these 1, 2, 3, 4, 5, 6 different energies that can be transferred into or from my or out of my system. And yeah, so E dot in would be like Q dot in plus then work, W dot in plus, now the mass part. The mass part is here. This is the mass part. Plus, but I might have like 3 inlets and 4 outlets, right? So once again, I need to define a summation over all my inlets, and on the other side here, the outlet, I need to have a summation over the outlet. So plus sigma in m dot times h plus v squared divided by 2 plus gz equals q dot out plus w dot out, and again, once again, the sigma summation over all the outlets, so let's say inlets and outlets, times h plus v squared divided by 2 plus gz. And that's it. How long is it? Okay, 30 minutes. I guess you need to take a rest, go back from the beginning, and just take a look over all I told you from the beginning here, the 2 different types of energy systems, then 6 energy transfers, and then total energy per mass, and then rate of energy transferred by mass, and I have 2 other parts in the other category, heat and work. and then here I added all those guys together, and from now on I'm gonna use this equation at the very end. And let's go and solve our example. Once again, let me go back to the example that we're gonna talk about here. This guy, it's a heat exchanger, and we have one inlet here, air coming down, and an outlet going out. From here we have the refrigerant entering the system and then leaving the system from the other side. So we have two inlets from top and left, and two outlets from below and right. Please keep this in front of you on your screen. Thank you so much, and let's go for the example. Okay, so as all, oh my god, sorry, I forgot to tell you here that that's you need to take a look at, that would be helpful to take a look at, yeah, I've mentioned that. So here, this page, note number 9, page 13. Thanks. So an example, as always, we need to define our system. This is like the first step that we need to take at the very beginning, and I'm gonna take the entire everything here, the entire block as my system. And here on top I have imaginary boundary, air coming in. On left I would like prefer to imagine it's all imaginary because I have like this kind of inlet, and here likewise on the right side. So all this wall I would take it as an imaginary outlet. It's just schematic. It doesn't I don't care. It's not different. And then on the below here I have another outlet through this imaginary boundary. So all the four boundaries are gonna be imaginary. So the system is gonna be the entire heat exchanger. And if you don't know what is the heat exchanger, you need to take a look at these pages on lecture note number 10, 6, 7, and 8. These pages to get familiar with heat exchanger. How does that work? So here's my system. All the boundaries are imaginary, so I draw them, these lines, as dashed lines. And on the left side I have mass and energy entering my system. I call this point as point 1. Here air was coming in, right? And I have m dot 3, I define here as point 3, and e dot 3. So here I have likewise dot 4, e dot 4. They're all dots because everything is per time. M dot 2 and e dot 2. Once again, let's look at that here. So air is entering the system, and it's carrying the energy with itself. And on the other side, it's taking all this energy out of the system. The refrigerant is entering the system, and it carries all those energies that we've talked about to the system, and then like carry them out of the system. So I have mass transfer and heat transfer, and energy transfer through all these four boundaries. Okay, and the question is, the problem asks for mass flow rate of the refrigerant, which is like, so refrigerants from left to the right, so it means like m dot 1 or m dot out, m dot 2. This is the question. Now before we continue solving, we need to take some assumptions. Is there any piston here? let's go back to the figure. Where is it? Here. Is there any piston? No. Is there any shaft? No. Any kind of like electrical work? No. It's just like kind of like a flow, the orange flow coming in and leaving, and then air coming in and just leaving. That's all. So I guess there's no work, right? Work is zero. There's no work transferred to the system because there's no tool which does this work. No piston, shaft, blade, pump, uh, like wire, heater, nothing. Is there any like fire, candle, stove, hot day, sun? None. So I think, yes, great. Heat is also zero. The heat transfer is zero. Okay, so someone might ask, well, wait a second. Heat transfer, heat exchange is zero. But how do you call this as a heat exchanger? Huh? Isn't it funny that you call something heat exchanger, but there is no heat transfer? That's stupid, right? But you need to pay attention. This is the trick. When we say there is no heat exchange or heat transfer, we defined heat and work and other types of energies. And then we said here transferred through imaginary what? Boundaries. Here, real boundaries. So when you talk about work or heat, they should be external, not internal. In this example, there is no sun out of the system. There is no stove out of the system or any source of like heat coming from out of this domain here, out of this box, which can like kind of transfer this heat to our system. There's nothing out there. But here there is the heat exchange between the air kind of like passing through these tubes and then leaving the system. Yes, the heat, the air is like warming up the refrigerant, right? So the refrigerant here, the color gets like sharper here. See, it's like darker orange, so it means it's hot. See, oh no, sorry, sorry, I'm sorry. So it's another way. So in the inlet the temperature is 90, but here at the outlet is 30. So the refrigerant is getting cooled down, the temperature drops, and the air, look at the temperatures, 27 and 60, it warms up. So there is like an internal interaction between the air and the refrigerant, but it's internal, and I don't care. I don't care what's going on in the system. I don't care what's going on between the elements of my system. I don't care. Whatever is going on, I don't care. I'm just talking about whatever passes through these boundaries. If it is electricity, does it pass the boundary? Does it cross the boundary? Yes. So include that in your solution. If it's not, forget it. If it's internal, forget it. Well, so let me write it here for you. So there's no work, for sure. Because there's no piston, there's no shaft, blade, compressor, turbine, I don't know, whatever that can do work, or like electric work, like a heater or element, or no, nothing. I mean, like the heater, and there is no sorry, there is internal heat exchange but we don't care. Really, I don't care. I don't care whatever is going on in my system. They might do whatever. Just interaction. The energy is transferred by these elements. So like air gives it to refrigerant. Okay, it's internal. Nothing is added to the system or nothing is withdrawn out of the system. Nothing crossed the boundaries. It's just internal. So let me put a note that we care about external heat transfer. Passing, or let's say crossing, the system boundaries. Okay, and a happy face. This is what we care about. External heat exchange or external work. And also kinetic and potential energies are negligible because see, there's no like the height difference. There's no height difference like this much, or even that might be a top view, so everything's flat. And nothing is mentioned about the velocity, so it means that okay, come on, forget it. So kinetic and potential energy changes are negligible. Let me rewrite my modified first law. Summation over energy carried by mass through inlets, H plus V squared divided by 2 equals Q dot out plus W dot out. Oh my god, it's too long. Plus sigma m dot. But it's worth it to write it at least one time on your exam. You know, you'll definitely write the solution correct and you'll get the point, so it's worth it. Kidding. So anyway, so based on all these assumptions, no heat, external heat, doop 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 doop, no work, goodbye goodbye, kinetic, bye bye, potential, nothing. Oh my god, so now it's a lot more easier, just these guys. That's it. Enthalpy. And enthalpy is a good guy. Enthalpy takes care of everything. Enthalpy takes care of internal energy, which is interaction between molecules, vibration, bonding, everything. This is internal energy. Plus, it takes care of the flow work, the P, pressure and stuff. I love enthalpy. Therefore, we can summarize this into m dot h inlet equals m dot h out. Great. Now, see, it's a lot easier. All we need to do we need to find our enthalpies mass flow rate. This is all we need to do. Happy. I'm so happy because I've canceled a lot of stuff up there. So why do I say enthalpies? Because here we have 2 inlets and 2 outlets, so we have 4 enthalpies in total and 4 mass flow rates. That's gonna be a mess. But wait a moment. We are gonna do cool stuff. Let me write my table. This is our famous table that I love, and you're supposed to love as well. Point 4. Point 3. Point 2. And point 1. I'm gonna summarize all the information here. Okay. Once again, point 1 and point 2 on the left and on the right are about refrigerant. Look at the picture on the example. Point 3 and point 4 are about air. Okay, so 1 and 2 are about what is it called? 1, 3, 4A, and this couple are about air. Okay. What do we know? We know that pressure here at point 1 is 1 megapascal. We know temperature is 90 degrees C. We know at point 2 we have the pressure. It's given in the text, 1 megapascal, and T2 is 30 degrees C. Point 3 we have the volumetric flow rate, V dot 3, which is 600 meters cubed divided by minute. It's not second. And P3 is 100 kPa. Okay. And T3 is 27 degrees C. Please keep in mind that we need to update this table through our solution just to keep everything here, keep all the data that we have and we find here to decide easier. 60 degrees C. Okay, good. I like it. Now what do I need? I need enthalpies. I need H1. Remember here, let's go back here, and here. I need enthalpies, and I need mass flow rates. I need H2, H3, and H4, and likewise the mass flow rates. But I'll talk about mass flow rates in future in like a couple minutes. Anyway, so we know that when we define our table, then we need to go through the points one by one and find enthalpies. So let's start with point 1. Okay, there we go. At point 1, which is here, the inlet for refrigerant. So I have pressure and temperature. Well, pressure and temperature, so it means I know the status of the system and of the state. I know the state, right? So let's go. What is the pressure? It's 1 megapascal, and T1 is it's 90 degrees C. So 1 megapascal. 1 megapascal. So let's go to the table for R 1 134 at 1 megapascal is 1000 kilopascal. So here they go. So the saturation temperature is 39.37. 39, but the temperature here, my temperature is 90 degrees C. It's much higher. So what does that mean? Yes, it means it's a superheated. It's superheated, right? So I need to go down to the superheat table, and at the top of all these blocks I have the pressure, which is 1 megapascal. Where is it? Here. See, pressure is 1 megapascal and the temperature is 90. There you go. There you go. What are we looking for? Enthalpy H up there. So come all the way down at that temperature. 32 here. There you go. 324.64 kilojoule per kilogram. So I know, so this is what I've done. I said that the saturation temperature at 1 megapascal was 39.337 degrees C, which is much less than 90 degrees C. So I made this judgment that it means my gas is hot. It's hot, right? It's hotter than the saturated vapor. So it means it's superheated. Because if it was a saturated vapor, the temperature was supposed to be that 39.37, but it's higher, so it means we continued warming up this saturated vapor, so we have superheated. And based on table 13, I found out that H1 should be 324.66 kilojoule per kilogram, and I need to update my table. There you go. Let's move on to another point, which is point 2. At point 2, which is the outlet of the refrigerant, once again, let's go to the table. We need to start with the saturation table. Here, again, same pressure, 1000. The temperature is 39, right? This is the saturated temperature, but T2 is 30, so it's cooled, right? It's subcooled, it's compressed. Or if we go to the temperature table, but for the same refrigerant, and check the saturation pressure at 30 degrees C, it should be 700, right? Right? It should be 700. It's the saturation temperature pressure, but our pressure here is 1 megapascal. It's higher than that, so it's compressed. So it's like, let's write it like based on pressure, because when you talk about pressure it makes more sense. So the saturation pressure at 30 degrees C was, I forgot how much it was, 770, 64 770 64 kPa, which is less than 1000 kPa, 1 megapascal, right? It means that I have compressed refrigerant. And in compressed refrigerant, we know that H2 should be it's same as the saturated liquid at the same temperature. It's about temperature, not pressure. So keep this in mind. It should be at the same temperature, and it's compressed, right? It's a kind of liquid, and when when you're talking about a compressed liquid, so the properties are the same at the same temperature, right? So that my property, which is enthalpy, is identical, is equal to the saturated liquid at the same temperature. It doesn't change that much. 93.58, because when you compress the liquid, well, it's not compressible, so nothing changes. So when you increase the pressure, nothing changes since you get to the saturated liquid. Just continue compressing. The properties doesn't change. But if you change the temperature, they do. They change. So as long as you keep the temperature the same, here's 30, I'm looking at that point, 30 degrees C, and I'm just looking at 30 degrees C for saturated liquid, so the properties are the same, but at higher pressure. I don't care. The temperature but should be the same. Anyway, so I got the H2 there, so I need to update my table. 93.58 kilojoule per kilogram. Great. Now let's go to H3 and H4. So at point 3, and 4, stop. Hold on. What's the material? It's air. And let me check the question. Did it say anything about like air enters and no? So they're not sensitive with like asking us to check the table for this gas, for air. We have the tables, we have enthalpy at different temperatures, but we can assume it's an ideal gas, right? It's just much easier. It's not as accurate as if we use the tables, but works. So why not? The material is air. So ideal gas. I love this part. Ideal gas, because it helps a lot, and then it's summarized. The solution will be shorter, and let's see what we're looking for, because I don't want to get lost. We are looking for here, so it's like the summation is m dot 1 h1 plus m dot 3 h3 equals all the outlets. This is how you need to keep all these in your mind. Don't get lost. You need to know what are you looking for. Okay, so H1 and 2 are done. We know them. 1 and 2. So if I take this guy there, then I would have H4 minus H3. So all I need is just the difference between enthalpies, right? So, and we know, please take a look at pages 3, 4, and 5. Oh my god, sorry. In this lecture note, number 8, and then you'll see that we can say H3 minus H4 per mass. It's little h. It's per mass. It equals to Cp. It's like heat capacity at constant pressure times T temperature differences. Okay. And according to table A1, the gas constant is kPa dot mq divided by kilogram Kelvin, and in table 2, I can find Cp, which is 105.005 kilojoule per kilogram degree C. Now I guess I have the difference between the enthalpies. That's gonna be easy. But there's one more trick, just one more step. We have 4 mass flow rates, m.1, 3, 2, and 4. But it doesn't make sense to me. Like, it shouldn't be like that. You know, it's a lot of unknown properties, unknown parameters. If you just take a look at this picture, although these two flows, the refrigerant and air, they're touching, I mean, they're just interacting energies, they're just transferring this heat, but they don't get mixed. So whatever refrigerant coming in leaves the system. So m.1 equals m.2. And likewise for air. Air is coming through the duct and then it leaves. Same mass, because mass should be conserved. And these, and air with the refrigerant, they don't mix, right? So I conclude that according to mass conservation, I know m.1 equals m.2, and that is the refrigerant mass flow rate that I'm gonna call m dot sub r. It's a lot easier to write it. And likewise for air, 3 and 4 are the same. It's mass flow rate for the air, and I'm gonna call that m dot a. Okay, I am looking for this guy. The question asks for this, the mass flow rate for the refrigerant, but still I don't know how much this is. Let's go to the table. See, this is why I was emphasizing on this table, because I don't want you to get lost in the example. I don't want you to lose time and just stare at the corner of the room and just think about, oh my god, I don't know what to do right now. I don't know what to look for. I don't know. If you have this table here, just go back there. It helps you. It tells you. So see, for air, we have the volumetric flow rate, and we're assuming that that's an ideal gas, and we have pressure and temperature. So according to the ideal gas law, equation, we have that PV equals mRT, right? And therefore V volume divided by mass equals RT over P. This guy is specific volume, little v, right? Therefore, little v equals RT over V. And I have RT and over P. And I have RT and P at 0.3. See, I have everything. So I can find little v. This is equation 1. And according to another equation that I have in my mind, that you need to have it as well, it's easy. M dot equals the volumetric flow rate divided by little v. This is the second equation. And do you know why? Because check this out. M dot equal little v equals volume over mass. And if I divide both per time, that would be V over T and M over T. And this is V dot over M dot. So take M dot to the other side and little v to the denominator. So M dot equals V dot over V. That's it. It was easy. So if you forgot, you can just start with this equation, divide by time, and then done. So based on equation 1 and 2, we'll end up with this, that m dot equals, well, no, according to equation number 1, v1, oh sorry, it's point 3 equals r t3 divided by p3 equals (861 meters cubed per kilogram). And equation 2 tells us that m dot equals, the v dot it's given, it's 600 meters cubed per minute divided by this little v that I just found for ideal gas, for air, and that's gonna be 696.9 kilogram per minute. We will finish this in just like 1 minute, just I promise, in 1 minute. So I have m dot air, okay, m dot air. So let's go up there. M dot a, don't be sad, be happy, we found it. So if I go to my equation here, I found m dot air, which is 3 and 4, and I got the difference between the enthalpies, and this enthalpy is 1 and 2, so I'm really ready to go. So if I substitute all these new parameters, point 1 was the refrigerant, so m dot r h1. Point 3, which is another inlet, is for air, was m dot a h3 equals point 2, it's the outlet for refrigerant, and point 4, it's the outlet for air. Okay, now let's take let's read take this term to the left and the other one, point 3, to the right. We'll end up with just a factorial. This m dot r factor m dot 1.1. So here I am factoring these guys. h4 minus h3. So m dot r, this is what I was looking for, would be m dot a times h4 minus h3. Look it up. Check this out. Where is it? Oh my god, I lost it. Oh my god. Oh, here. Right, I have CP, I have both temperatures, divided by h1 minus h2, and I've got both at my beautiful table, there and there. Therefore, it's going to be a long calculation. M dot r equals m dot a, I just found it, 696.9 kilogram per minute. It's just math, please hold on, and it's gonna get finished. So h4 minus h3 was the ideal gas thing, so the CP, which is that, times the difference in temperatures, T4 minus T3 degrees C, and I have H1 minus H2 that I have calculated before. 93.58 kilojoule per kilogram. So m dot r equals 100 kilogram per minute. Let's play with the units. Dun, dun, dun. So kilojoule and kilojoule gone. Okay, good. Kilogram and kilogram, goodbye. And this kilogram goes up there, and minute. Oh, and degree C. So just kilogram per minute here. Oh, wait. Sorry. Anyway, so that is what I was looking for. Thank you so much for watching. Let's go from the example here, since we started here. So we define our system, then we said what we're looking for. The question was the mass flow rate, m dot for the refrigerant at point 1 or 2, they're the same. There's no work, no tool, nothing, no reason for kind of applying this work, no heat transfer, nothing. External heat transfer, kinetic and potential were 0, so the modifies first law equation summarized into this guy, and then all we needed to do was to find enthalpies and the flow rates, mass flow rates. So we created this table, and we wrote all the unknowns and the questions in red to make it clear for ourselves. Then we made some judgments here, superheated or compressed, and then we found the enthalpies for refrigerant. Then for the air, we assumed it's an ideal gas. We use PV equals MRT, and then the difference in enthalpies equals CP times the difference in temperatures. Then we solved for the mass flow rate for the air, again based on this formula, PV equals MRT here, this guy. And then we solved for m dot mass flow rate here with the use of volumetric flow rate and the specific volume. And then we just substitute, we just put everything that we found so far in this main huge first law equation, and then we found the mass flow rate. Again, thanks for watching this lecture, and let me tell you something, that this equation was really hard and it was complicated. But the reason that I picked these comprehensive examples is to cover most of the subjects, right, for you, and talk about most of the subjects that I can. It does not mean that you will be evaluated based on another example at the same level of difficulties. So on the exam, there's not going to be an example like this. That was super difficult. So don't freak out. And thank you for watching this lecture.